So today we're going to look at hashing, which you're going to see in multiple lectures in this school today, next week, and and I would think that many of you would have heard this term at least, maybe even implemented it, used some hash tables in Python, Java, or whatever. But we're going to look at it in the language we have been talking about, right? In theory, probability, complexity, and so on and so forth. Okay. So, what is a hash function, right? So, it is a function which takes from a large universe elements and maps it to a small table T. Okay. So, I am going to assume that the size of U is some P. I will tell you in a few minutes why I am calling it P, and size of table is T. I do not know others will use the same notation in the other lectures, but you can do your translation otherwise. Okay. So, first why is this going to be useful in this algorithms for data science? Well, typically when we have some stream of elements and we want to store something about them, right, that has been the theme in small space. Now, if I want to store an element of U, how much space would it take for me? Right, space to store an element of U. Can somebody tell me how many bits do I need to store? Log? Log P, okay. Log P bits, because P is the size of the universe. So, for example, if I want to represent a number between 0 and 1024, how many bits do I need? 10 bits, right. So, it is log of that size. So, to store an element of U, I need log P bits, and by the same token, if I want to store an element of T, it will be log T bits, and U is going to be, or P is going to be much larger than, right, T. T is a small table and P is my large universe. So, for example, you might think of compiler table or something, and you want to take all words used by your programming language and map it to some 20 cells or something like that. So, T is like 20, whereas U can be very large. Okay. So, it makes a big difference between log P and log T. So, if in the stream of elements I want to store some information about every element, instead of using log P bits, if I somehow do some mapping and store, instead of x I store h of x, I will use only log T bits. So, that is a big advantage. Okay, that is the way we will use it. But what is a big disadvantage? If instead of storing an element of U, if I store its image under h, if I store instead of x, I store h of x, okay, and I just argued that h of x takes very less space, so that is good. But what is bad? Exactly, right. Multiple elements from U can get mapped to same element necessarily, because P is much larger than T. So, a function which maps this large universe to the small table will not be 1 1. So, it is going to map a lot of elements into one particular element. So, if you store this, then I will not know whether h of x represents x or y or z. There are many things that get mapped to this h of x. Okay. So, that is a disadvantage. Okay. So, now we have to be careful. So, we want, so now let us talk about what are the good things I want of this h function, right. I want, okay. So, some features I need of h. Small probability of so there is a word for it, multiple elements get mapped to the same element, collision, exactly, right. So, in the hash function terminology, I want small probability of collisions, right. So, that of course, the tool we are going to use to deal with this is randomization, okay, that is what we have been seeing, and we will do some probabilistic analysis. So, we will, instead of storing x, we will store h of x, and somehow if the h has the nice property that it does, it has small probability of collisions, that is good for me. What else do I need? Well, I want h to be easy to compute. Right. If given an x, I should be able to compute h of x easily. What else do I need, right? So, let me come back to this, the space argument I said. So, instead of storing an element, I am going to store h of that element. So, let us say this entire stream somehow, whatever I want to compute, instead of storing x, I am going to store h of x. I also need to know h, right, to be able to compute. So, in my structure or the solution I am going to have, I have to have h, and every time when an element comes, I can compute it and store h of x. So, h also I am going to store it in my structure. So, I want the space for h to be small. Right, this small, easy, these are all very, very subjective terms. We will make things precise as we go along. Okay. So, so now I am going to think in terms of finding functions which has these nice properties. Okay. Now, U is this universe which is coming, I have no control over. Okay. Somebody is giving me this user defined data. So, now imagine that whatever h I can think of, h will have collisions because h is mapping large set to small set, and an adversary can choose in a way that I say, hey, I have this beautiful nice h function which has all these nice properties. I mean you will come back and say, look at this set, you choose your h, I am going to come with the set where all elements are mapped to same location for this set in h. If that is my user defined set, I am stuck, right. There is no small probability of collision and so on, because worst case, given any h, somebody can come up with the set where all elements get mapped to small number of locations. So, there is a huge collision happening, right. And so, to defeat against that kind of an adversary, we do, what do we do? That's what we have been doing, right. So, let me go back to another analogy, right. Quicksort. Let us say, think of a deterministic quicksort where I say, I choose the first element as the pivot, right. It is a deterministic algorithm, no randomness in the algorithm. Choose the first element of the pivot, do your partitioning and recurse, that is quicksort. Clearly, there are bad input for this, which will result in your n square running time, because adversary can keep a sorted list and every time your partition really does not get you a good split, and it will result in n square time. So, to deal with that, what did we do? Randomize. So, we said I am not going to pick the first element as the pivot, I am going to pick a random element as the pivot. Now, this random element can be anything. So, an adversary does not even know, right. If you know the adversary can come up with the worst case input, no, because we by doing this is a very important difference or advantage of randomized algorithms you should know. Building in randomization into the algorithm as opposed to doing an expected analysis of quicksort over all permutations, the randomization is into the algorithm. So, there is no fixed input for which this quicksort is bad. Even randomized algorithm is bad, right. Even randomized algorithm, its worst case is n square. But what does it mean by worst case is n square? Worst of what? Right. Randomized algorithm, randomized quicksort algorithm also is n square in the worst case. What does it mean? Worst in what sense? Yeah. Random choices of the pivot. Based on that, so that is something internal to the algorithm for every input. So, there is no input for which it is bad. For every input, there will be a choice of pivots for which it is bad. Okay, so that is what makes the randomization built in, so that an adversary cannot play against it and give a worst case input. So, similarly here, whatever hash function I think of and I publicize it, an adversary can come and give me a worst case input and say, hey, on this for this function, this input will map it to one location or few locations. So, there is a lot of collision and you are not saving much. So, we are going to randomize it. So, how do we randomize it? I am going to have a family of functions, family of hash functions, and then I will randomly pick from that family. Okay. So, that is the way we will randomize it. So, we will now talk about a family of functions, right. So, let us call this goes with a lot of names. So, 2 universal, sometimes 2 universal hash family, right. It is a family. So, this is a family, is going to be a set of functions, not one function, set of functions from u to t with the following property. For all x comma y in u, x is not equal to y, probability that f of x equal to f of y is pretty low. Okay, so what does it low means? So, I am going to say it is at most 1 over cardinality of f. Okay, is it 1 over cardinality of f? I think so. Yeah, we'll figure it out. Yes, it is. So, what I am saying is, okay, what is this probability over? I mean, the moment I say probability, you should ask me what is the random experiment you are doing, right. So, what is the experiment I am doing? That I pick a random function h from f or f. Yeah. So, I want to say that the number of functions. So, another way to interpret this is that you give me an x and y which are not equal. In this family, the number of functions which will map both x and y to the same location is at most 1 out of the number of functions in this family. Okay. Is it 1 over cardinality of f? I am not.
Because you want to be distributed across the table. So maybe you want 1 by.
No, that is the uniformity thing. So, that what you are looking for is, if you are given x and a y in T, what is the probability that h of x equal to y? Okay, or x will be thrown uniformly into any of the locations equally likely. That is not what you are talking about here. I am talking about collisions. Okay, so maybe I think it's 1 over T, you are right. Okay, okay. For a different reason, we will see. Yeah. Yeah. Okay. So, I'll come back and repeat this. So, another way to think about it is, yes, f of x is a particular location in the table uniformly. So, it is 1 over T as the probability. F of y will also get mapped to that location as the probability 1 over T. So, the product is 1 over T square for any particular location, right. So, now add over all the locations, it is 1 over T. Okay. So, for any particular, so this is too universal. Pairwise, we will come to pairwise independence. That is one of the things I am going to talk about, and it just says that f of x to one location, f of y to another the same or another location is the product of these probabilities. Okay, let us not get confused about it. This is what I want. Okay, so what this says is that among this family of functions, the number of functions that will map x and y to the same location is at most 1 over T fraction of the functions. Yeah. Right. 1 over T fraction of this. So, this is a definition anyway. So, why bother? I mean, I am going to define it this way, and then we will see the use of this definition, that I am going to call this. So, it has this, the property A is what is spelt out now, the small probability of collisions. That is what I mean here, right. So, if I pick so basically, if I want a good function h, what I will do is, if you give me such a hash family, I will pick a random function from this family, and that has the nice property that probability that any pair of elements get mapped to the same location is at most 1 over T, and this 1 over T is my measure of small probability of collision. Okay. First question. So, we are going to, first of all, we have to address a lot of questions here. First of all, is there such a universal hash family? And number two, so what is the use of such a universal hash family? How does it help the space thing which I was talking about earlier, and all of this as we go along. So, this is the central family we are going to talk about. Okay, is the definition clear? What is the what? So, it is pairwise universal. So, this is for, I am talking only about the pair of elements that get mapped. Now, if you just extend it to more than 2, then that is a different game there. Yeah, the 2 stands for 2 elements that get mapped to the same location. Right, there is a K universal we will come to at the end. Yeah. Okay. So, now first of all, is there such a universal hash family, and does it have the other nice properties I wanted, B and C, easy to compute, space to store, H to be small, right. Is there a universal hash family? Yes. Suppose, okay, so let me see. Existence or construction, okay. So, suppose I say all functions from U to T, right. Suppose I just take the family of all functions from the set U to set T. How many functions are there? Can somebody tell me? Right. So, I have this U and T. Let us say I just pick all functions from U to T. How many functions are there? because u is of size p and t is of size t. T power p, yeah, p power t, okay, let's try. So t power p, p power t, any other answers? And then we'll see which one is. But I'm impressed at least that you guys got this, one of the two, which is so. So why is it t power? Any, yeah. Yeah, so it's p power t or t power p? T power p, right? Each element of the universe has any of the t choices to, because I am not saying 1, 1 on 2 and all that. That's another interesting question you can think about. Number of functions. How do I specify this function? I just have to give the image of every element in the universe, then the function is specified. Okay. So, there are p elements, and if you tell me the image of each of these elements, you have specified the function. There are t choices for each image. Okay. So, that is t power p is the number of functions. Okay. So, now if you just talk about my C, the space to store H, how much space does it, if I have to just store this function H from this family, how much space does it store, does it take? Well, it is P log T, right. Any function is like P log T width. That's really large. That's a no. Okay. I mean, I will also argue that that's a universal hash function. I haven't done that. Let me do that first. But so if I ask you, is there a universal hash family? Yes, there is one, which is a set of all functions. But I'll quickly tell you why it's universal. That's not very hard to check. Once I tell you that, then the space is too much. Anything, P is my universe size, and anything which is like proportional to the universe size is too much. I can't afford that. So that's why it is a universal hash family, but not good enough for me. Okay, why is it universal? Let's go back to the definition and see what is, again, I already sort of walked through. What is the probability that f of x equal to f of y if I pick a random function from this family? So again, probability that f of x equal to f of y equal to some one particular element k, let us see, right. We are talking about all functions. So, f of x has how many choices? If you pick a random function, it has t choices. So, it is going to map to k with probability 1 over t. Similarly, f of y is going to map to k with probability 1 over t, and these are all independent. Okay. So, it is going to be 1 over t square, and so there are t choices for k, and you do some linearity of expectations, and then you will see that probability f of x equal to f of y is equal to summation k going from 0 to t minus 1, 1 over t square. So, this is 1 over t. Okay. Because what is inside the sum is independent of k anyway. Right. So, there is a all functions is a universal hash family. That's good enough in terms of being universal, but it's not good in terms of space. Okay. So, what I am going to argue is that there is a small sized universal hash family, 2 universal hash family. That's very good. That's also easy to compute. It requires a bit of number theory and modular arithmetic, nothing much, and it's easy to compute, small space, small size, universe, all the nice properties I wanted. So, that's going to be what we will spend the next few minutes talking about. Questions? No, I just gave you this family. Family of all functions is one family which is universal.
Okay, sir, but first you asked, right, how we have to check whether the family exists or not.
Yes, and that question was in the previous slide, and I answered it in this slide. Okay, because I said this is universal. So, this family is universal because it has this property, whatever I have written down in red. The only thing is it is too large a family, so it takes too much space to store it. Okay, so now I am going to give you another family which is small sized, easy to compute, and all the nice properties you want. Okay, and that family is not very hard. So, now I will tell you why I called my universe as size is p. Any guesses? Why did I call the size of the universe to be p? I am going to assume it is a prime number. Okay. So, okay. Now you should question me, what? Universe is user defined, how can you assume something about it, right? Right? So, universe is some n elements are given where I have to define my function. How can I assume it is a prime? Who can answer this? So, what I will do is I will extend it to the next prime and I am going to define it over larger set of elements. Okay, you do not want it, that is fine, I want it. So, I am going to define my universe to not just your n elements up to the next, somehow assuming prime is good for me, it has some nice properties. So, I will extend it to my next possible prime and I am going to define my function on that. But again, now you should ask me, oh, the n has become very large now. Can it be very large? Thankfully, we know there exists a prime between n and 2n for any n. Okay. So, it is not very large, it might become at best or at worst it might become 2n, that is all. Okay. So, this is useful. So, my universe is now size is a prime number. So, here is my family. What is my family? I am going to define this family is equal to H A comma, it is indexed by two numbers A and B. A, B, yeah. So, it is in this ZP star as they say, or ZP 0 to p minus 1, except I do not want A to be 0, B can be anything between 0 and p minus 1. So, that is my family. Well, what is HAB? I will define HAB. It takes an element x from the universe and it just simply does Ax plus B mod P. Okay. So, think of it as some sort of a permutation it is doing. It takes an x, it multiplies by A, adds B and does a mod P. Not good enough, I need to do something more. Why? What is the range? So, what is the range of this function? What is the range I want? 0 to t minus 1. So, what do? I do a mod t. Okay. So, any element x from the universe comes. So all I need to, okay. So, Ax plus B mod P mod t. That's all. That's the function, family of functions. How many functions are there in this family? P square or a little less, because a is not allowed to be 0, right. So, p into p minus 1. Okay. Contrast this with the size of this family, which is t power p, right. So, we said all functions, it is too universal, but it is too large a family, t power p, and storing that is p log t base, that is too much. But I am going to give you another family which has only about p square elements, and so space to store is like 2 log p bits. And now I will argue, again it is not at all hard, that this is good enough, this is too universal. So, it has all the, and it is easy to compute, look at the function, right. All I need to remember is a and b, it's just one multiplication, one addition and 2 modulus computation. So, it's easy to compute, small space. Now, I have to prove to you that it is too universal. Okay. So, in some sense, it's a small size family which has the power of all functions. So, as if you are picking a random function from a set of all functions, it has a power in terms of this probability of collisions to be small. Okay. So, now the claim I want to prove, that this family F is too universal. And remember what that means, what do I have to show? I.e., for all x comma y in the universe, x not equal to y, probability that a random function, and let us say f is picked uniformly at random from this family, then probability that f of x is equal to f of y is at most 1 over t. That is what I want to show. In other words, a number of functions in this family which will collide a pair of unequal elements is at most 1 over t. Okay. So, it has the power of the family of all functions, but the family size is very small. Okay. So, let us so f, what is, if I have to know f, what is, what do I need to know? Look at this family definition. A random function from this family is means what? A random, B random, that is all. Right? That's another thing. Again, we are going to see later on other lectures where we will say pick a random hash function. Okay. That looks like a very strange statement. How do I pick a random hash function? Now it is clean. Oh, I just have to pick these 2 integers at random, right? A from 0 to p minus 1 to p minus 1, b from 0 to p minus 1. Pick them random and you got a random hash function f. Okay. So, we will show that the number of functions. So, pick let. So, proof x from the universe okay, let ax plus b equal to some r, ay plus b equal to some s. That is, this means that HAB of not quite. Okay. So, I will just, because there is another mod t computation I need to do to get HA of B R. Okay. So, suppose this. Where the f which I randomly picked is this HAB. Okay. So, from R and S, I am trying to see, can I figure out what is A and B? Okay. Okay, this is mod P. In the mod P world, let me do some subtractions. So, what do I get? A into x minus y is equal to R minus S. All I am doing everything in the mod P computation. So, which means that A equal to x minus y inverse into R minus S. Sorry. Okay, no, what do I want to say? Okay, so suppose R is equal to S. Okay. So, this function mapped x and y to the same element in the mod P world. Okay, not mod T world, we have to check. Of course, they will be true in the mod T world also, but this function mapped x and y to the same location in the mod P world. Suppose R equal to S, what can you say? Well, you have A into x minus y equal to R minus S, which is 0 in the mod P world. So, what can you conclude from here? Okay. 0 to P minus 1 is a field. I have a product of two numbers which give me 0 in a field. So, either A has to be 0 or x has to be equal to y. Okay. This is where I use the fact that P is a prime. So, in a field there are no 0 divisors. So, A has to be 0 or x has to be equal to y, but we know A is not 0 and we know x is not equal to y. So, this is not possible. So, what does that mean? So, contradiction I would say, or not possible as A is not equal to 0 and x is not equal to y. Okay. So, what have I established? I have established, so think of this line 0 to P minus 1 and I picked some A B and and here is an x and here is an y, and I hope this picture helps. So, x gets mapped to somewhere by this HAB, right, Ax plus B mod P. Y gets mapped to somewhere else, and what I argued is that where they get mapped are always distinct. If x and y are distinct, where they get mapped. So, x gets mapped to R, y gets mapped to S, they are distinct. Okay. This is the first observation, that in some sense the A comma B mapping, what it does in the mod P world, it just sort of like a permutation, because if A and B is random, it somehow randomly changes the value, but they are all distinct. They cannot collide in the mod P world. Of course, there is a mod T that is taken later, we will come to that later, but for now what I have just argued is that pick any function A B, it does not have collisions in the mod P world of any two non-distinct distinct elements. Okay. So, now what do I want to compute? I want to compute this number of this A comma B such that HAB x equal to HAB y. X and y are distinct. I want to compute the number of functions that map them to the same location, right. That is the for this universal statement I need to show that HAB x equal to HAB y, the probability is at most small. This is same as saying the number of functions f What do I need to show? This number of these functions is 1 over t times the total number of functions. Okay. So, to compute this probability, I can compute it this way, that just compute how many functions will map x to y, and I argue that 1 over t times the total number of functions. That is what I have to show. Okay. So, what I have shown is that in the mod p world, your x and y are not going to go to the same place, but in the mod t world, of course, they may go to the same place. Okay. So, let us see. This is, so I am going to write this as number of pairs r comma s, r and s are different, but they are same mod t. Okay. I may be confusing, but it's not very difficult thing at all. What I am saying is your x and y in the first round, when you do the mod p computation, let us get mapped to r and s, and I argued that r and s are different. R and S, in fact, as you vary x and y, r and s are going to be some vary in this number line 0 to p minus 1. So, really the number of functions that will map x and y to the same location is the same as number of pairs r comma s, which in the mod t world they are the same. Okay. So, this is what I want to compute. R and S are different, but in the mod t world they are same, because R and S, it so happens that they are HAB of x and HAB of y, but you might as well think that they are some arbitrary pair of numbers which are distinct. Okay. So, now let us compute this. This is very easy to do, right. So, basically R and S in the range 0 to p minus 1. So, let us fix R. Okay. So, again let us go back to this line 0 to p minus 1. When I do a mod t, this is 0 to t minus 1. So, let us break it up into blocks of size t, and suppose my r is here. Okay. Let us fix r. R has p choices, any of the 0 to p minus 1. How many s's are congruent to r mod p? No. Let us be careful. R and S are distinct in the mod p world. How many values of S are congruent to R in the mod t world? Right. So, for example, suppose R happens to be 5 mod t. Then you look at somebody who is 5 mod t here, R and S would be congruent mod t, and somebody who is 5 mod t would be congruent to R, 5 congruent to R mod t, and so on and so forth. So, how many such candidates are there? P mod t minus 1. Yeah, somebody else said something. Yeah, P by t, 1 in each of these blocks, right. If somebody R is congruent to 5 mod t, then the 5 mod t element here, so think of this as 0 to t minus 1, 0 to t minus 1, 0 to t minus 1. So, that whatever that element in the p line, that element would be congruent to R in the mod t world. So, there is 1 in each of this block which would be congruent to R. You cannot take it same as R. So, it will be p by t minus 1, exactly, good. Yeah. So, this number, I am going to write this as R has p choices, S is other than R with the same mod. So, it will be, I am going to say floor of p by t minus 1. Okay. So, this is p into, let me less than or equal to floor of p by t, I am going to say p plus t minus 1 by t, it's rounding up. We are rounding up because p may not be a multiple of t and so on. When I round it up, I may add at most t minus 1, and there is minus 1, and this is equal to this one and that one. I am going to cancel it. And lo and behold, this is exactly what we wanted to show. What did we want to show? That number of these functions is cardinality of f by t. What is cardinality of f? That is p into p minus 1. Did I show that? Yes. Okay. Good. Questions? So, is that clear? So, the key thing which we really used is that in the mod p world, R and S are different. That is all. And this is because p is chosen as a field. P is a prime number. So, in this, A, B, all it is doing is somehow putting things in some sort of an order. So, if A, B is random, then you're just think of it as you're doing a random permutation of your elements, and then you're doing mod T. Okay, so this is probability that this H A B of x, where A and B are chosen at random, is equal to H A B of y is at most 1 over t. This is 1 over t fraction of the total number of functions, which is p into p minus 1. Okay, so this is very powerful construction. I mean, very simple but powerful. It simply says that this small sized family somehow behaves like all functions from u to t. So, if I want to randomly pick a function, you do not have to pick from this all function, pick from this function, at least from the point of view of achieving this 2 universality, you have this. Okay, now let me give you a acute application of this. And then we will extend to k universal. Okay, I will just k universal, I may not prove or do anything, I will just say what the function is and we are done with it. But here is a nice application, and that is, you already saw yesterday this problem of max cut, right? No, max cut also in the tutorials, right? Oh, you use the term min cut. Okay, let me define it and do it. Okay. So, min cut is also interesting, max cut is also interesting, but they have contrasting algorithmic behavior. So, I will tell you more about both. So, let us talk about cut, right. So, your input is a graph, undirected graph with vertex set and edge set, and what is the goal? Find a partition of the vertex set such that, so S is contained in V, T is contained in V, S and T are disjoint, and S union T is equal to V. So, I just want a partition of the vertex set such that the number of edges across the cut, right, the size of this set u comma v, u in S, v in T, this cardinality, well, is maximized. This is max cut. You can also talk about minimized This is min cut. Right? One of these problems is polynomial time solvable. Which one? Have you seen this? Okay, you may or may not have seen. So, min cut can be solved using max flow. Anybody has seen max flow min cut theorem? Okay. Menger's theorem is a variation of it. Yeah. So, but you have seen flows, max flow. Anybody else who has seen max flow? Okay. So, you can talk about an ST cut where networks in algorithm in the advanced algorithms, typically initial course and algorithms may or may not cover it, but the second course and algorithms should cover max flow, min cut theory, or even a graph theory course, right? Graph theory course should cover that. So, you can talk about an ST cut where S is a small specific vertex in the graph, T is a small specific vertex in the graph, and now you can talk about separating S and T, or the partition where small s in capital S and small t in capital T such that minimum number of edges go across. Now, this can be solved using powerful application of max flow. Okay, max flow can be solved in polynomial time. This is one of the beautiful algorithmic or graph theoretic questions using which you can solve this in polynomial time. So, when I say this is solvable in poly time, I mean the ST cut problem is solvable using max flow, but then you try all possible small s and small t and you can solve min cut in polynomial time. There are other ways to do it as well. Max cut, on the other hand, is NP complete. Again, I think I already asked this. How many people have seen NP completeness? I'm not going to ask about it. Huh? You have a general knowledge on NP complete. I'll ask you about it in the break. How many others have heard of? Okay, good. So, at least you have heard of NP completeness. So, it's believed that NP complete problems cannot be solved in polynomial time. This is one of the famous open problems in computer science. We don't know it, but it's widely believed that you may not have an efficient algorithm for an NP complete problem. So, in particular, if I want to find the partition which maximizes the number of edges across, that is a hard problem. So, what we are going to do is to come up with some sort of an approximation algorithm for it. Okay. So, that means I may not be able to find that partition that maximizes the number of edges across, but give me some partition which gives you a lot of edges across, okay, and that lot has to be quantified appropriately. Okay. And so, yesterday you saw a randomized algorithm, right, Udlak? You saw a randomized algorithm which does something, which gives you a partition where anybody wants to complete, we followed. So, what we showed is that there exists a partition of the vertex set such that at least so many edges are across the cut, m by 2, half the edges on expectation. There is a randomized algorithm. I will repeat it again, that there is a randomized algorithm. So, okay, so approximation for max cut. So, first what we will show, so finding the optimum is hard. So, I want something close to optimum, right. So, I want a algorithm which is fast, polynomial time, it should give you a cut that is not very bad compared to the optimum. But I don't even know optimum is, so how do I know how bad it is to the optimum? We'll compare it with some sort of a bound for the optimum, okay, and say if the optimum cut value is 200, I will produce you something which is at least 100, okay. So, I am never more than, not worse than half of the optimum, okay. So, that is the goal. So, the first claim is there exists a cut with at least m over 2 edges, okay. And how did we show this? We have seen this yesterday. So, what is the partition? I have to partition the vertex set into 2 such that at least half the edges go across, okay. So, what partition should I do? Yeah. No, my goal is to come up with S and T, right, this S and T. So, give me an S and give me a T, and then we will try and argue that, oh, how many edges are going across this. And of course, first thing you should ask is give me the graph, right. But I am going to say for any graph, there is a generic way of getting S and T. We are doing randomized algorithms. So, what? Sorry? Yeah. So, what does randomly mark mean? So, what do I do? More precisely, yeah, that is the idea. For every vertex, I need to figure out whether it should go to S or T. How do I figure out? Yeah, but just tell me a little more precisely what do I do to figure out whether I should put it in S or T? Yes, random is correct, but when you want to really implement it, what do you do? Toss a coin, right? Or consult a random number generator to give me something 0 or 1 or something between 0 and 1. If it gives me less than half, I will put it in S. If it's greater than or equal to half, something, right? Basically toss a coin. If it comes head, put it in S. If it comes tail, I will put it in T, right? So, that is my random partition. So, the partition is clear. Right now, we are going to talk about randomization, randomized algorithm, randomized partition. So, the partition is, so uniformly at random, put x in S or T where x is a vertex in the graph. So, for every vertex, I will toss a coin. If it comes head, I will put it. Let us assume I have a fair coin, and based on this random toss, I will put it in S or T. Okay. Now, let us see how many edges. So, I have gotten my S and I have gotten my T, randomly partitioned. Now, I want to understand how many edges are going across. That will be a random variable, because this partition is random. So, I can only talk about the expected number of edges going across the cut, right. My interest is an edge like this. So, given u v in edge, what is the probability that u v is in the cut? I haven't defined really cut, but I hope you understand. This is equal to probability that, when is u v in the cut? When u in S, v is in T, or u in T, v in S. What is the probability of this happening? 1 by 4, okay. Why is it 1 by 4? Half into half plus half into. What am I assuming here? Why is it half and half? So, So, u in S, v in T is 1 over 4. Sorry, so it's half, right? Yeah, why is it 1 over 4? Let's be very careful. U in S, V in T. I am assuming that these coin tosses are independent. But if you look carefully, I don't need full independent. All I care about is this pairwise independence. That if you pick any pair of, this is the two universal thing. If you pick a pair of vertices, their coin tosses are independent. So, u in S, v in T has a probability of 1 over 4. Similarly, the other probability is 1 over 4, and I use union bound, and I get 1 over 2 as the probability that this edge is across the cut. Okay. The key thing to note is that I am using pairwise independence. Okay, I should have talked about this in the hash family thing. I'll come back to it later again. Okay. So, now expected number of edges in the cut. What is this? Why? Summation uv in E, expected or probability that uv is in the cut. Which we argued it to be half. So, if there are m edges in the graph, then the expected number of edges is m over 2. Okay, and the key thing to note is that for the analysis to go through, all I needed was this coin tosses are pairwise independent, because it is this step, probability u in S, v in T, where we are measuring what is the probability. This is the product of these two probabilities, half into half. All I needed was this pairwise coin tosses to be independent. Okay, now I claim that I have proved the claim. Is that true? What I wanted to show is that there exists a partition which has at least m over 2 edges. But what I really showed is that I did a random experiment, and I said in this random experiment the expected number of edges across is exactly m by 2. Does the claim follow from that? Can somebody give me an argument why? So, I say hence there exists ST such that number of edges in the cut ST is greater than or equal to m over 2. Okay, and you've probably seen this probabilistic method in the tutorials. So, it is very useful observation, but not very hard to argue. All I am saying is, hey, if the average mark is 45, there must be somebody who got greater than or equal to 45. How can the average be 45? If everybody got less than 45, the average will be less than 45. So, the expectation is average. What is the expectation over all? Really, if you think about it, the expectation is over all possible partitions here. So, if the average over all possible ST partition is m over 2, there must be one partition where the number of edges is at least m over 2, because if everybody is less, the average cannot be, that is all. So, there exists a cut where the number of edges across the cut is at least m over 2. Okay. So, now our goal is to find such a cut. Okay. And I am going to give that as the solution of my approximation algorithm, right. My goal, remember, is to design an approximation algorithm for max cut, which is at least not too far from the optimum, right. So, maximum can be m all, maybe the whole thing is a bipartite graph, all edges are across, there is a partition where every edge is across. So, M is a maximum, but I will find a really, I'll find a cut which exists in any graph by this claim. I'll find such a cut in polynomial time and say that is my cut and that is my approximation algorithm, which produces you at least half optimum, right? That is my goal. So, the goal is to find such a cut deterministically in polynomial time. If you want a randomized algorithm, here it is. I know, just do a randomized experiment, but I claim that you can actually find a deterministic algorithm using two universal hash family, which we came up with, right. So, where is the randomness here? And I want to get rid of the randomness. Where was the randomness in this partitioning? Coin toss, right, to say whether I should put it in S or T. Instead of coin toss, I am going to use my universal hash family and get the coin tosses, whether it is a head or a tail. I am going to use my universal hash family, which will give me this coin tosses. I will use that and then argue what I need. Okay. So, de-randomizing the algorithm, the above algorithm. Okay. So, now I am going to use this family HAB. Okay, I should have indexed from U to T as I defined before, but now my universe is the graph's vertex set and my table is going to be 0 1. Okay. So, what am I doing? So, what is this function doing? This function takes the vertex set V and assigns some of them value 0 and some of them value 1, okay, which defines a partition. Okay. So, take this two universal hash family, right. I have choice of U, T, I mean that family is very general, defined for any U and any T. So, let me define it for my vertex set and 0 1 is my range. So, it gives me a partition. Let us understand the two universal property. So, what is the two universal property I know is that for all vertices U V, where U is not equal to V, probability that, what did I call HAB? U is equal to HAB of V is at most what? That is the number of functions, but in terms of probability 1 by T. What is T? 2 for us. So, it is at most half. Okay. So, this is pairwise. So, now, so this is that is all. I have given you an algorithm. What is my algorithm? Take a two universal hash family here, let us call this, I have been calling everything F, let us stick to it. It just assigns every element a 0 or 1. So, that is my coin toss outcome. Okay. So, that gives me a partition, and the property of this partition is this: if you pick a pair of vertices, the fact probability they get mapped by any function here is at most half. Okay. Good. So, now let us do our analysis. So, how many edges are there? So, this at this moment it looks still like a randomized algorithm. It is a randomized algorithm because your H is random. It is a randomized algorithm. So, now let us look at expected number of edges in the cut. Okay. So, I hope it is clear. So, what I am saying is I pick a 2 universal hash family where the range is 0 1, that defines where the domain is my vertex set, that defines a partition of the vertex set into 2 sets, that gives me a partition. Now, I look at the cut across and look at the expected value of the cut, where the expectation is over all the functions in this family, right, because H is a random function. Now, it is the same argument. If you pick any edge, what is the probability? So, yeah, I want to compute this. Let us say uv is an edge. What is the probability that uv is in the cut? Yeah, can somebody tell me? Probability is uv is in the cut is the probability that u and v get different values in the partition, in my coloring, in my coin toss, whatever. If u and v get different values, u goes here, v goes here, or v goes here and u goes here. They should get different values, then it will be in the cut. What is the probability that they will get different values? Why?
Because probability of both being hashed to the same location
Is at most half. So, the probability that they will get different, because we know that the probability that they will get the same value is that they will get into either both in S or both in T as the probability of at most half. So, they will be split is the probability at least half, right, 1 minus this. So, that is greater than or equal to half. So, now expected number of edges in the cut is greater than or equal to m over 2. Okay. This is not yet de-randomization. It is still randomized algorithm because I picked a random hash function from this family. But the nice thing about this family is that this family size is small. What is the size of this family? What was the size of the family? Let us go back here. No 2 power. Where what is the size of our universal hash family? We defined, right? This was the size of the family. P into P minus 1. Just P into P minus 1. Mod? Number of vertices, sorry, mod V into mod V minus 1. Well, this may be little more because I have to, P may be larger than V. P is a prime. Now, size of V may not be a prime, but it may be like 2 times V. Whatever it is, it is order n square. Okay. The number, because that was a big thing, we made a thing, right. The total number of functions in all functions is huge, p power t or t power p, whatever, I forget. But this small family has a similar behavior in terms of collisions, and the size is only p square, right, where p is the domain size, order of the domain size, and for us it is just the vertex set. So, it is order n square. So, I am going to say order v square, which is like n squares, number of functions are there. So, now let me see. So, what have we shown is that take this family of some n square functions and pick a random function from here and give your 2 coloring, the partition, and expected size of the cut is already as good as you want, at least m square, at least m by 2, Okay. Expectation now is on this small sized family, right, which means that there is some function in this family which will give you a cut of size at least m by 2. I can do brute force and compute it, right. So, this implies there exists a function f in this family f, and if we use f to partition V to get S and T, the cut value of S and T is at least m over 2, right, because earlier I said this claim there exists a cut, that partitioning was with over all random functions, right, the all functions, that's too many and I don't want to do it, but quickly what we realized that pairwise independence is what we really care about in the analysis, and so a 2 universal hash family can give you pairwise independent bits, use that to do your partitioning, and then in that family the expected size, if you use a random function to do your coloring, is at least m over 2, and so now you can de-randomize it. How do I de-randomize it? So, find it by brute force, try one by one, right. So, try all order n square functions in F and pick the partition that gives the largest. To get a cut of size at least m by 2. Okay, any questions? I'll just take 5 more minutes to. So what, just to summarize what we did, we defined this 2 universal family of hash functions, and the collection of all functions is 2 universal, but that's too much, too many functions, too much space to store it, and I argued that there is a very simpler, using some little bit of number theory, there is a small size family of 2 universal hash functions, which is easy to store, easy to compute and all that. We are going to see a lot of applications of this later on in this big data world, especially when I want to represent element not by an element, but by its image of a function. But here is a very nice application to de-randomize an randomized approximation algorithm. I'll just spend 2 minutes or 5 minutes to just say what is K universal and and say that there is a K universal hash family, can also be defined very similarly, and that's also useful. Okay, so maybe I should. Yeah, so K universal family. So again, you have a family F of functions from U to T. I didn't define 2 universal this way, but this is also another way to do it. Maybe that's for tutorial, which is that for all x1, x2, some xk in U, all distinct, and y1, y2, yk in T, probability that when I pick a random function, h of x1 equal to y1 and h of x2 equal to y2, is exactly equal to the product of the individual probabilities. Okay, I did not define 2 universal this way, but you could also define it this way. Maybe that's something for the tutorial to check, that an equivalent definition of 2 universal would be that if you pick any pair x, y and a, b, probability that x equal to a and y equal to b is equal to the product of the probabilities that x equal to a times probability x equal to. So, this is also, you know, equivalent to this k-wise independence, like the pairwise independence, this is k-wise independent. And again, you can,
You should still say that each of this is 1 by 2.
I think it follows. I may not need to say it, but yeah. So, that is the uniformity thing. And there exists, so what we can do is this function h or a1, a2, ak for defined by a1 plus a2x plus a3x square plus ak x power k minus 1 mod p is k universal. Okay. So, maybe this can be looked at in detail in the tutorial if there is time. So, the key thing to argue this is this yeah. So, we argued that if x and y are different and a, b are from this field, then ax plus b and ay plus b are different, right. So, if or there is a so what we can do is if x1 gets mapped to y1 in this polynomial function and x2 gets mapped to y2, x3 gets mapped to y3 and so on, there is a unique h which will do this mapping, okay, because you can do this inverse like exactly what I did. So, if r and s are fixed, then x and y are fixed kind of argument you can show that. So, there is this van der Waals matrix you can write to solve this system of linear equations, invert it and you will get your original thing. So, for number of functions, number of a1, a2, ak which will map to y1, y2, yk is unique once you give x1, x2, xk, and that is because this system of linear equations has a unique solution. Okay. You may not have followed or I may not have said everything correctly. If there is time in the tutorial, you can deal with it. Otherwise, it's a reasonably straightforward generalization of 2-wise independence. So, the size, instead of p square, it will be like p power k or something. And that is useful whenever you are looking at k-wise independent family, of random variables, then you want to say that such a family generates you k-wise independent family of values, random values. Okay.